Good morning, everybody, or good afternoon, I guess, for those of you on the East Coast. I am Mike Graley with Pack International, and I have joining me now our new acoustician, Drake Hentz. So I'm throwing him into the deep end with the webinars. Gonna have him help present this new product with me. So today we are here to introduce a new product. It is the RSIC Adapt. And this is, get my mouse clicking over here. So RSIC Adapt provides spring performance with RSIC 1 simplicity. And we're going to talk about all those things and where they come from. This is a new product that we are launching. This is patent pending. We got a lot of cool stuff coming with this thing. So first, let's talk about where this gets applied, where you might use this, right? So this is an alternative to springs. So where we use springs tend to be high-end spaces, right, where we're going for high levels of sound isolation. Maybe it's a gym, we've got spaces underneath that we're trying to isolate, or we've got a spin class and we've got spaces up above that we're trying to isolate, or maybe it's a high-end home theater, movie theaters, recording studios, high-end condominiums, all of these different kinds of things, right? So in these spaces, we're going for high levels of sound isolation, but also because these are fancy spaces, they tend to have more complicated ceilings, right? And so we have a lot of different finishes that we have to deal with. We have elevation changes, soffits, coffers, all of these kinds of things. And we also have higher expectations for the level of fit and finish in these spaces as well, right? And all of those things combined makes doing springs for these spaces really complicated, and it makes it take a lot of time. We have right now working, while we're here talking, a full-time engineer on staff, Ty Fitzgerald, who just does spring shop drawings for us. So we've done a lot of these, right? Here's an example of one of these and kind of the level of complexity that you might get into spring shop drawings. And we talked about this in the past, in the springs webinars and whatnot. On the left, here's the part of the spring layout. This isn't even the entire thing. This is a sound stage in New York City that we did a while back. So each little colored dot on that is a different spring, right? And the different colors represent different load capacities for the springs. And we've got to use those different load capacities because we've got different ceiling loads depending on what's there, how much drywall we're holding, all these kinds of things. And so we have to go through this level of detail. And then, if we've got elevation changes or things like that, right? The framing for all of this gets complicated. The loading gets complicated. So sometimes we'll draw up 3D Revit details like this one on the right. That's this little column detail that you see circled in green. And then here's what that looks like in the field, right? This is this same project. This is a mock-up that I got to go see because I was out in the Northeast in Vermont for NoiseCon. So took a little side trip to New York to go walk the site. So they did a mock-up of this space. You can see there on the left, you can see the spring hangers. And then on the right, we have how the contractor decided to mark this one out, right? So they went and spray painted little dots for the different springs, right? So it's just kind of like a paint by numbers, so they could get all the springs in the right position for this. And then here's not quite the finished product, but the ceiling is almost finished here, right? So you can see this big, huge space. They have this lighting truss that was, hung independently of the ceiling. You have this elevation change there at the back of the picture on the right. And then you have the sloped ceiling over there that you can see in more detail on the left, right? So we had to figure out just the hypotenuse of this, the extra, length of drywall that's not shown in the RCPs. Just like a lot of complication that goes into all of these. And we can do it, but it takes a lot of time and it makes the projects go slower because we have to get all this information in order to do these. And so as we kept going through this, I kept thinking, and we all here at PAX kept thinking, there's got to be a better way to do this. If only we could provide this high level of performance, but make it like a RSIC 1, where it's just just need this many of them. Oh, what's your ceiling weights? Okay, use this spacing, you're good to go, right? There's got to be a better way. And that's how we came up with the Adapt. So you see that over on the left as the actual isolator, and then on the right, you see it installed in the test lab. So we're going to go and talk about the isolator, and we'll talk about all the acoustical testing too. But before we do that, let's talk about springs. Why do we need an alternative to springs? What are the issues with springs? So first, one thing to keep in mind is just construction timelines, right? Contractors, whenever we're talking to contractors, we're like, hey, when do you need this? The answer is always 5 days ago, right? And with other, more common acoustical isolation products like Resilient Channel, RSIC One, these kinds of things, there's a network of drywall distribution yards all over the country. These dots here are some of our distributors that we work with that carry, RSIC Ones and other pack products. But like Resilient Channel, you can pretty much go into any drywall distribution yard and they'll have it in stock sitting there. I mean, you can even order it online from Home Depot and get it delivered to you the next day, right? RSIC Ones, we have a bunch of distributors. Many of them stock ours. We also have some of the big drywall distribution companies have, distribution hubs that stock large quantities of RSIC Ones and they can send them quickly to their, local stores. So presumably a contractor, especially in a large metropolitan area, can walk into a drywall distribution yard, be like, hey, I need 1,000 RSIC clips, get them that day, walk out and go start installing them, right? And with springs, the issue isn't like stock of them, the actual availability of the product. Like we have them in stock pretty much ready to go. We do a final little bit of assembly and quality control checks before we ship them out. That usually doesn't take that long. That's not the sticking point. The sticking point is that you have to go through all of this work to do the engineered shop drawings, right? That's the big lead time thing with springs. That's the big bugaboo, right? Is all the time that it takes to produce this, right? The shop drawing on the left, and then the time that it takes for the contractor to translate that drawing on the left to the markings in the field on the right. And just to give an idea of the scale, like, the spacing between these kind of the blue, white, and the red, blue, there in the foreground of this picture, that's probably like 4 foot. This little sector I think is right there where that green circle is. So you can imagine just the amount of time that it took to go mark out that entire thing. And the odds of not missing any one and getting like the red and the blue switched or these kinds of things, right? So why do we have to go to all of this effort for springs, right? Why can't we just say, oh, well, just here's your ceiling weight, kind of calculate the ceiling weight per square foot, figure out your coverage for a spring, say it's 4 foot by 4 foot spacing, so it'll cover 16 square feet, multiply that by your ceiling weight. That's the spring capacity that you need. Contractors would love to be able to do that. And over the years, we've had a lot of contractors that have called in and said, hey, I need 200 of your 80-pound springs. And we're like, no, not the way it works. We need all of this information from you so that we can do the shop drawings and then tell you what springs you need. And they're like, no, I know what I'm doing. I've done this before. Like I got this, just send me 200 of the springs. And occasionally they would argue with us long enough where we would just give up and we would say, okay, fine. Here you go. Here's 200 of the 80-pound springs. It won't work, but you say it will, go for it. And then weeks or months later, we get a call from them and they say, hey, why isn't my ceiling flat? This thing didn't work. I was like, well, yeah, because we told you that we needed to engineer the shop drawing so that you would get a flat ceiling. And then we go through that whole process, send them a new set of springs, they install that, and then they have a flat ceiling. Right? And the reason that we have to go through all of this, like, sure, I think as like acousticians, we think, oh yeah, we need to make sure that all of the springs are equally loaded so that we have optimal loading for acoustical performance for all the springs. And sure, maybe that kind of matters, but I think if you kind of even just look at the theoretical isolation efficiency curves, even going from like 1 inch to 1/2 inch of deflection, there's not that big of a change in your theoretical isolation efficiency. And Drake will talk later about like why that also doesn't necessarily matter as much. But really the big thing that people are really going to notice is if the ceiling is flat or not. And remember, these are high-end spaces, right? And there's high expectations for the level of fit and finish, right? And so the reason that we specify steel springs is for their deflection, right? It's that 1 inch of deflection that gives us a natural frequency of 3 1/3 hertz, right? That then gives us, in theory, isolation down to very low frequencies, right? But it is also that deflection that creates all of this complexity, because when you have 1 inch of deflection, that's 1 inch of potential height variation in your ceiling. And if you get a spring that's old, you might get more than 1 inch of deflection. So you have potentially more than 1 inch of height variation in your ceiling. So that's why we have to go through all these sort of like load calculations and do all these shop drawings to make sure that we actually get a flat ceiling. And if we have point loads or heavy things at the perimeter, we make sure it doesn't sag or sag in the middle, all of these kinds of things, right? So it's the primary reason that we specify springs that creates all of the complexity. And so it means we need all of this information, right? We need reflected ceiling plan to know where the ceiling is, ceiling height changes. We need floor plans, HVAC. Oftentimes we're holding the ductwork too. We need electrical or AV because we're holding lights and speakers. We need building sections to see where, structure is that we have to avoid. To see where there's, again, elevation changes, details. Maybe there's like curtain pockets that we have to work with, things like that. We need joist locations. If we're doing these on a wood framed assembly, we're often trying to line up the isolators with the joists. On that layout that I showed you before for the soundstage, it was an existing steel frame. As much as possible, we lined up all of our springs with the steel purlins so the contractor didn't have to add additional framing. We also need information about a bunch of materials, right? We need to know how much everything that we're holding weighs so that we can include that in our load calculations, right? That's the ceiling layers, it's also lights, speakers, ductwork, all kinds of things, right? And it takes a lot of time to get all of this information and go through and coordinate all of it. And for you acousticians, you can think about it like doing an HVAC noise analysis, right? Where you have to get all of the information about the mechanical system in order to do your analysis, right? And you can imagine, how well that always goes, right? Like every time that you ask for, the octave band or third octave band sound power data for the air handling units, like you get that quickly and you get a complete set of it, right? Like, no, you'll get like the overall A-weighted sound power level. And then you're like, no, I need the octave band data. And then you'll get like, the inlet sound power data, but not the outlet or the casing radiated. And there's always all this back and forth, right? And then by the time you get all the information, like it's changed or it's not what's in the submittal, right? Like this is all of the complication that goes into doing spring shop drawings, right? And this is why it takes so much longer than just, using RSIC clips or other isolation products. Okay, so fair enough, right? You might say as an acoustician, like, okay, I get it that it's complicated, but these are high-end complicated spaces. Like that just comes with the territory, right? And, as the acoustician, my job is to recommend the assemblies and the products that will get the level of, acoustic performance that I think is necessary for this project. And then it's up to the rest of the project team that has expertise in all of these other areas to implement those designs. But what then happens is as acousticians, we often wind up designing in a vacuum. And, I was an acoustical consultant for 10 years. Like I did this too. I'm not trying to like call everybody else out. Like I did this a lot too. And when I started here at PAC, I was talking with Elzo about, acoustic designs and assemblies and things like this. And I was like, yeah, we were talking about fire ratings and UL. And I was like, yeah, but the UL part, that's not my problem, right? That's the architect's problem or that's somebody else's problem. I'm just doing the acoustical design. And Elzo just about lost it because he's like, no. Like that's why they don't pay attention to you acousticians, is because like you're ignoring all of these other things that are important on a project, right? And you do that at you do yourself a disservice by ignoring these other things. And so you wind up making recommendations for products and assembly designs that can't be implemented. And so we have to take into consideration these other things. Now, as an acoustician, it's not our job to, do a fire design or something like that. And we certainly don't want to take on that liability. I would not encourage any of you to do that. But you need to be aware of these factors so that you can make better design recommendations and design decisions, right? And, here's an example. This came in just this week. Here's a project. And this is a truss. I think it's a wood truss, but it's got steel web members, right? So there's a spring underneath this, screwed to the bottom of this fire rated design. This spring is not in a UL fire rated design. They've got seismic bracing wires that go down to the bottom. They're not shown as slack, right? So they've short circuited the isolation here. They've got a spring with a 3/8 threaded rod that then they show going to a resilient sound isolation clip or RSIC clip. You can't fit a 3/8 threaded rod through the ferrule of a RSIC 1, right? You can't attach this to the bottom of a joist like that. That's not allowed for fire. Like there's a whole bunch of things in here, right? For fire, seismic, constructability, all of these different things that make this not work, right? And so now the contractor comes to us. We got this from the contractor. They're like, hey, I got this. I can't build this. What do I do? And so now we're making recommendations, right? And we always try and go back. Like Mike sent an email to the acoustician earlier today. It's like, hey, we got this. We want to make sure you're included in this conversation. We try and include you in that conversation. But like that doesn't always happen, right? And so then the project team goes and starts making other decisions that don't include your acoustical expertise. So this is where I come in on the spaceship, right? So this is why I've been doing all of these webinars, right? Like as I've been at PAC, I've been learning all of these things about construction and fire and, you know, cost and lead times and things like that. And I've been trying to share that information because I've realized that I was missing out as a consultant in these designs by not including these things. And so I'm trying to share that information as much as possible. And with the Adapt, we've tried to take all of that information, all of those things that we've learned, right? Like this is the culmination of all of the stuff that I've learned here over the last 5 years at PAC about construction and fire and things like that, that I've learned from Mike and Elzo. But not just my 5 years, but the 50 years that Elzo has been in business. You know, back in 1976, Elzo and his wife Carmen started their own drywall contracting business, right? And Elzo has owned his own business in construction and a whole multitude of different businesses over the course of those 50 years. So this is the culmination of 50 years in construction, and you know, for PAC, you know, about 25 years in construction and acoustics specifically, and me almost 20 years in acoustics, which is kind of hard to imagine. So in all of this, like PAC has worked at sort of the nexus of the acousticians, the architects, the distributors, contractors, structural engineers, fire protection, UL, all of this kinds of stuff, right? And so with the Adapt, we have tried to bring all of these things together to create a solution that works not just acoustically, but for all of these other sort of elements that go into construction to make sure that we have a product that works well for everybody, right? And so that's why we have the RSIC Adapt, a better way to do high performance sound isolation. But why is it better? What's the key thing, right? So the issue with springs, the thing with springs that creates all of this complexity is the deflection. So the question is, can we reduce the deflection somehow, do away with that while still maintaining the acoustical performance? So we have used a foam isolator, right? A polyurethane foam isolator. This is the same foam that we use for our PAC IFB, our floating floor isolators, which we've already got test data out there for. You know, many people are speccing those, recommending those, using those on projects. So we're using that same foam. And the benefit of this is that for very minimal deflection, so here you can see your load deflection curve up on the top graph. So sort of the ideal load, loading about 10% deflection of the free height, about 2.5 millimeters for a 1-inch or 25 millimeter foam. So less than 1/8 of an inch. But with that, you get the isolation efficiency shown below. So in theory, you get isolation down below 20 hertz. So over the full audible frequency range, right? So we can get good levels of sound isolation with minimal deflection. And 1/8 of an inch is usually within sort of like the flatness tolerances for ceilings and things like that, right? So a negligible height variation. So we understand the issues and the complexity with springs. We understand that that's deflection. The foam isolator and the RSIC Adapt eliminates the deflection as an issue, but we're pitching this as an alternative to springs, right? So as acousticians are like, well, how does it perform? I want to see the test data. Saying spring performance. So Drake, take it away.
Yeah, thanks. And good to be here. Good to be with PAC. If I haven't met you, hi, my name's Drake. I'm a longtime viewer, first-time presenter here at PAC. So it's great to be here. I came on board, and this was kind of one of the first things. They were like, hey, we got this new product coming out, and it's got spring performance. And me coming from an acoustical consulting background, I was like, bold claim, prove it, prove the spring performance. So they had already put a great plan in place, and I'm on board. So that's what this section is for. So what we did is we took it to Maxon's acoustical test laboratory, and we put it like an apples to apples comparison between this new RSIC Adapt and our spring and the industry standard Kinetics ICC spring, which you see pictured here. And this red line is where your ceiling would fall to, by the way. So the Kinetics would drop 1 inch from that deflection. PAC's spring would drop 1/2 inch. It comes pre-compressed. So we were already kind of trying to solve some of these issues with the springs, and we had great results there. And then ours would drop just kind of nominally. This RSIC Adapt would drop nominally the 1/8 of an inch, not perfectly to scale. So yeah, take that with a little grain of salt. But so yeah, here it is pictured. We took it to the lab, and we wanted to get our numbers. So next slide here is, this is our RSIC Adapt, STC 70, IIC 65. We were very happy with these results. This is where, you know, a lot of manufacturers out there would see this, be happy, take this, slap it on a box, put it on their website, and call it a day, you know, reap the rewards. But we went a step further. We had this whole test assembly, or test series against springs. So we wanted to stack them next to each other. And actually what we found was kind of a rank order where they all got STC 70. And there were some noticeable differences in the IIC rating, where we tested right between the Kinetics spring and the PAC spring. So that was really exciting for us to see, and is why it's a product today. It's why we're doing this webinar. It was a proof of concept that we were very excited about. Oh, Norrell might not be seeing slides.
Yeah, Steve's been working on that. I think.
Great.
Yeah. Can other people see the slides? I assume that Steve and Mike would have jumped in and told me to shut up and fix things if they couldn't see the slides.
Great. Yeah,
great.
We got them. Thanks.
You're good. Okay. All right. Cool.
Thanks,
everybody.
Cool. Yeah, so we were stoked to see that we kind of tested right between the two springs that we tested in this test series. And just to kind of cover our bases here, we did proper layouts for these springs here on this next slide. This is the Kinetics layout. And this is kind of back to what Mike was talking about. You need to get the right rated springs with the right load calcs and distributed evenly so that you get the flat ceiling. So this is the test layout for the test we did at Maxon with the Kinetics ICC. And we were able to just take basically the engineered layout that we would do with springs and do a 1-for-1 replacement with the Kinetics, or sorry, excuse me, the RSIC Adapt. And so there was not nearly this engineering effort that had to go into that, which is again the big benefit here. Yeah, we'll get there to the low frequency performance. So yeah, next we go dive into the third octave.
I'll interrupt real fast.
Yeah.
I just want to make sure it's stated explicitly that for the RSIC Adapt, all of these were the same load capacity, so there's no variation. This is the same isolator for all of these positions here. Whereas with the springs, we had the layout where we had the varying loads, because the point of this is that you don't have to do shop drawing, so you can use the same thing everywhere, right? And I'll let you keep going, Drake.
Yeah, no, you're good. So kind of, I'm sure all the acousticians here, what they've been itching to see is not the single number differences. You know, here at PAC, we don't stop at single numbers, just like the acousticians have been itching to see. So here you can see our ASTM E90. This is the STC test that we did at the lab. There's some lab flanking going on here, specifically in like the 125 to 400 hertz, where you kind of see the 1-for-1 agreement. But then we actually test a little higher in the mid to high frequencies with the Adapt, which we were excited to see. But again, we're hitting lab flanking limits, so these both got that STC 70. Next, we did IIC, wanted to get the impact noise, and you can see there's a little more nuance here than might have been readily available with the single numbers. The Adapt tested, which is noted here as VI, PAC RSIC VI. But this is the blue line is the Adapt, and there's some interplay. You know, we do better here, they do better there. But what we're really trying to prove, and like the proof of concept here, is that it's comparable to springs. So this was still really encouraging. And so then we moved on to the rubber ISO ball. This is a European test standard. You take like a big, heavy rubber ball, and it's like a medicine ball, but a little bouncier, and you drop it on your test panel, and then do a bunch of math and normalization and get your results kind of like you would do with some other tests. And you can see some of that interplay disappears here. And there may be a little bit more of a difference at specifically this like 400 to 630 frequency octave bands. But a lot of the rest of it is within test variability, and we're hitting kind of that sound floor at the top end. So this was still really exciting for us to see. And we followed this up with the heavy hard, which is like this heavy soft, but with a hard metal shot put. Not officially standardized, but Mike is working on that as we speak. Well, not as we speak, but later today probably. And yeah. So that's underway, and we went ahead and tested that while we were there. And you can see kind of a similar story here. They might be doing a little better at 400 to 630 hertz, and the rest is within variability. And but again, we wanted to follow this up with our own springs just to maintain completeness, and we found, yeah. So RSIC Adapt, in some weird exceptions, might not be as good as springs, and maybe there's an argument to be made there for why you should use springs in very specific cases. But still, we like our springs a lot, so it looks pretty good on the graph, and we're pretty excited to see all that. Yeah. So spring isolators, this was my big thing. So Mike presented me with all of that when I first came on board, and was like, "Are you convinced?" And I was like, "I guess kinda, but this is one test on one assembly. Like, I want to see more. I want to see, open web truss. I want to see mass timber. I want to see all the other assemblies you see on a day-to-day basis, let alone, variations in your ceiling construction and in your insulation in your cavity." And what I've been learning a lot about is there's all these spring tests, which aren't as many as there should be, but they all kind of come back lab flanking limited. So like, how many tests do you need to do where you get kind of inconclusive results because you just keep hitting this flanking limit before you're convinced, And so they're difficult to test because of lab flanking. So there's not tons of testing out there. If you go dig into the existing testing from all the different manufacturers, there's just not as much as you might want. And because it's so difficult to test, a lot of our testing is aging out. So if you go look at the dates on some of those test reports, you'll see that they're, 15 to 30 years old sometimes. And the Gypsum Association recommends sunsetting data, acoustical performance data at 30 years old, which a certain kinetics spring test that has very good results turns 30 next month. So that's notable. And then the ICC G2 recommends sunsetting it at 20. So how much data are we relying on that is actually kind of should have been sunset by now? And how different are building materials and practices now compared to then when they were tested?
Yep.
Yeah, exactly. So we have kind of a lack of testing, like just because of some very, very practical limitations and some tricks that we need to learn how to get around, I guess, as a whole acoustics community. But then we go to our theoretical performance, and we're like, okay, but springs are the best isolation because of this single degree of freedom theoretical isolation. And what we find is that doesn't pan out quite the way we would think either. We approached Jerry Lilly and chatted with him about this because he's done some insertion loss testing on a bunch of springs, and you find there's a departure of your idealized single degree of freedom insertion loss and what would actually be measured kind of around 100 hertz, which is where a lot of our acoustic metrics kind of begin in the frequency range. And a lot of that has to do with surge resonance, and you have these surge frequencies where the spring isn't isolating anymore; it's actually resonating, and then you just kind of see a departure of those predicted versus actual. And this can be its whole own webinar, and there's plenty more digging we can do on this. So if anyone's interested, there's certainly more to talk about here. But yeah, so that's kind of what the prompt was to get away from springs and move to this foam. Yeah, I'll throw it back to Mike here.
Back to me. So I see there's a lot of questions in the chat, and I just responded to this about like, well, what about wood framed or steel or these kinds of things, right? And I have a lot to say about that, but we're gonna get through this, and then we'll come back and we'll talk more about testing because we're gonna have some time for discussion after this. Okay. So we talked about there's issues with springs. There's all this complexity with springs, right? Now we talked about the comparison of the acoustical performance, right? But really the reason we created the Adapt was not to create an isolator that did better than springs or something like that. Like that wasn't the acoustical performance wasn't the issue, right? It was all of the construction complexity that came with the thing that we used to get the acoustical performance, right? So we've talked about the spring performance. Now let's talk about the RSIC 1 simplicity bit of this, right? So here's the adapt, right? And it's called the adapt because it's adaptable. No more long convoluted acronym names for PAC, though we'll still stick lots of letters at the end of this, so don't worry. But we've got lots of options with this, okay? So we have a steel box frame with these flanges on the side where it says side mount there, right? So got a hole at the top where we've got a bolt that we can put through it. So that's our top mount. So that allows you to mount it underneath a concrete slab, a composite deck, any of these kinds of things, right? Where it's a typical top mount. But using the same frame, the same box, potentially the exact same isolator, even with the bolt coming out the top, you could use these pre-drilled holes on the side to mount it to the side of a joist, 2x10, an I-joist, open web truss, whatever it may be, right? And we've done projects in the past, some high-end homes where this is a house in the Hamptons. There's like a whole wellness spa wing of the house. This is ridiculous. And in the middle of this room, there's a beam that goes down. On one side of the beam, it's concrete on metal deck, and on the other side, it's like I-joists, right? And so this isolator, you could use the exact same isolator, top mount on one side, side mount on the other side, right? So you've got all of this flexibility. You got the foam isolator that's in here. That's the thing that gives us the benefit of the minimal deflection, makes it easy to get flat ceilings. We have a fire stop, right? So PAC, as you all know, we spend a lot of time thinking about fire and UL designs and all these kinds of things. We have not gotten this UL listed yet, but we will go through that process. It's a long and expensive process, and we're just starting down that path. But that will come. So we have this fire stop here so that in the event of a fire, when things get really, really hot and melty, if the foam loses some of its structural integrity in a fire, right, you have this big steel sort of like U-shaped washer on top. So if that foam compresses, you then get metal-to-metal contact, and that minimizes the potential drop for your ceiling, right? Because you want to minimize the stress on that drywall, because the drywall is your fire protective membrane, as I've talked about a lot in other webinars. We also have this uplift stop, which is the nut and a washer on the bottom. And so when you go to install these, which I've done a number of times now, building lab construction and all these kinds of things, if you've got a spring here, typical construction for these spring ceilings a lot of times is you have a cold roll channel, which is a 54 mil 16 gauge steel that goes into the clip on there, and then you screw hat channel to that, and often it's like a 20 gauge 30 or 33 mil steel, right? So this is heavy gauge steel. So then you have a self-drilling screw with a little screw tip that'll drill into the steel, and so you got your screw going and you're pushing on the thing trying to get it to go in and bite and go through, right? And if you've got a spring that doesn't have any bump stop on it, it's moving out of the way, right? And even if you've got a bump stop on there, right, which we do on our spring, that's why we pre-compress ours, is to reduce this motion, and we've got a bump stop on our spring. But if you're pulling down on it a little bit, or like the ceiling's already loaded some in other places, so you've already got some more deflection on that spring, you've still got all this movement in there, and it just makes it harder to install. There's hardly any movement, right? An eighth of an inch of deflection. So that ceiling's just staying there really solid. It's so much easier to just install this, right? And if you think about like the time savings over each one of those screw connections that you get here, and then also for the drywall, screwing that to the hat channel, and that over the course of a ceiling the size of that soundstage that I showed you earlier, that's a huge savings in labor, just making it easier to screw it in, right? And then we have the bottom mount, and we have a whole bunch of different attachment options for this, right? Because here at PAC, we're thinking about the contractor that comes from, Elzo's experience and Mike's experience in the drywall world. So we have all of these different attachment methods, and I won't go into all of these and what they do, but we've got a bolt at the top, we've got an eye nut at the top, so you can do a wire drop. We can do our easy clip that allows you to snap the cold roll channel into it. So much easier to install than trying to thread the cold roll channel through the bolt and a C clip, as is typical. We also can do a wire eye nut at the bottom of that, so you can drop a wire that way, all these different combinations. We also have a swivel head that we'll offer with this, so that you can get that if there's some offset in terms of, the mounting point is over here and then the attachment point is over here, you've got some offset, angular offset there. And then there's more, right? There's other things. If you need to do a big drop, like they did in that soundstage project, right? It was threaded rod, these huge, 10-foot long drops of threaded rod in some cases, probably. You can use a coupling nut and just have more threaded rod. You could, over on the right, you could put unistrut on the bottom of this. right? Either to do a trapeze so that you can hang your ceiling underneath. If you've got a duct that's bigger than you can span with the cold roll channel, you can use unistrut and then drop your ceiling from that. We're doing that on a project right now with springs. Or you can hang mechanical equipment off of this, all of these kinds of things. There's a whole bunch, and I'm sure we'll come up with more. Mike's probably come up with 2 more while I've been sitting here talking. We'll keep going through all of these versions, right? We're still in the early phases of this product. Another interesting thing about this is because of the lack of movement in here, and because we've got these side flanges on it, I think it allows for easy adaptation for seismic restraint. Now, we haven't gone through and had like seismic engineering done on this, but again, that's another thing that we're going to do. But you can see here in my kind of like quick little sketch, you can have the housing, you can have your uplift strut that reinforces the threaded rod. That comes down to the housing, right? The housing is not the isolated thing. It's the U-shaped washer and then the clip that comes down below that that's actually isolated. So anything that goes to the housing is fine and can be rigid, right? So you can have taut cable restraints that go to that. There's already holes that you can tie them to or connect them to. And then you can have that uplift strut. And then there's very little movement at the bottom, and we've got this metal-to-metal restraint, constraint around the isolator. So you can have your acoustic isolation, but also have seismic bracing here. All right, so in summary, the Adapt provides spring level performance, great acoustical performance, but with minimal deflection, so less than 1/8 of an inch. That makes it easy to get flat ceilings. So you figure out what your ceiling load is, you use one isolator, you get a flat ceiling and good acoustical performance. And that means no shop drawings, which is a huge time savings. That means one isolator type or load for an entire ceiling. So we don't have to do all of those layouts. The contractors don't have to go spray paint a bunch of dots on the floor to figure out where all the things go, right? You can just lay this out like you would a normal drywall grid ceiling. Everywhere you'd put a wire, you put an Adapt. Also makes it easy to make adjustment in the field, because we all know that what gets built in the field is exactly what's shown on the drawings, right? Like, no, that's not the case, right? And a lot of times with springs, we're holding ductwork, right? And the ductwork's shown on the mechanical drawings where it's going to be, but when it's hidden, it often moves, right? If the installer for the fire sprinkler pipe gets there first, they put their pipe where they want so they can get nice runs and gentle bends and all this kind of stuff. And then all of the trades that come after that have to deal with that, right? We've all gone out to projects where we see there's this pipe and then there's this weird bend in the duct, and you're like, why is that there? It's, well, because the sprinkler pipe went right where the mechanical contractor wanted to put the duct, right? So all these things shift around. And with springs, if there's big shifts in these things, we have to adjust our layouts in order to accommodate those. With the Adapt, you don't have to do that. You can just move the Adapt over or add another one if there's extra load, right? It makes it so much easier to adapt to this in the field. See what I did there? It's easier to install too. You don't have to accommodate the ceiling drop under load, right? So with springs, if there's no pre-compression, you've got 1 inch of deflection when it's fully loaded. So you can think of these situations, right? Like maybe in condominiums where you've got your structure and then you've got this almost like full height window, right? And you've got this tiny little space for your ceiling to sit before it actually goes and is like into the glass or into the, the like aluminum header of the window, right? And so you got to get your ceiling to land perfectly in that space. When you've got 1 inch of deflection, right, that takes up an extra inch of ceiling height that you can't deal with, you can't get out of the system, right? And it just makes it really hard to get that ceiling to land exactly where you want it. With the Adapt, where it sits when it's installed is where it's going to land when it's fully loaded within, 1/8 of an inch, which is, construction tolerance usually. And then the ceiling doesn't move as you push up on it. It makes it so much easier to install. The other thing that Mike pointed out to me just the other day as we were talking about this is like with the spring ceiling, say you've got a 1 inch deflection spring and it's, your loads are all designed for 2 layers of drywall, right? So you install your first layer of drywall, right? So you get half of your deflection because you've got half your load. So it deflects in 1/2 inch. And then you want to caulk your perimeter because you're going for high levels of sound isolation. So you want to caulk both layers of drywall. Well, if you caulk that first layer, then when you put the second layer on, the whole thing drops down another 1/2 inch, right? So then you're just pulling all this caulk, or if the caulk's like dried, it starts to kind of pull your drywall. It just gets weird and funky, right? So it's really hard to seal both layers of drywall on a spring hung ceiling. With the Adapt, you don't have that movement, so it's easy to seal both layers. You get better seals too. Because it's one isolator to rule them all, distributors can stock it. So we're back to a RSIC 1 world where a distributor can have these in stock. Contractor shows up, say, hey, I need 1,000 of these for this big project, and they can walk away with them that day, right? It also means that contractors can pre-purchase this. So we've got a project going on right now where there's a lot of design, another complicated thing. We're doing spring shop drawings. Contractors in a hurry to get things going, and this project's on the other side of the country, so it's longer shipping time. And so they're like, hey, can we pre-purchase springs? You give us an estimate of all the different quantities that we need. We'll order some extras, and then when you give us the drawings, we'll figure it out from there. And it just adds a lot more coordination to make sure that they've got the right ones. We're going to start with one floor and then work our way through other floors, right? Makes it more complicated. In this case, contractor can pre-purchase these, figure out kind of like the general ceiling loads, get the right isolators, pre-purchase that, have them sitting ready to go whenever it's time to start the construction of the ceiling. So stop designing in a vacuum and break out of your vacuum acousticians. Work with the rest of the project team. The Adapt is designed to allow you to incorporate and better adapt to all of these other sort of construction things: fire, seismic, constructability, cost, lead times, all of these kinds of things. It simplifies all of those while still giving you the level of acoustical performance that you're looking for. So in summary, springs are often our go-to for high levels of sound isolation, right? But the thing we specify them for, their deflection, is the thing that creates the complexity. And complexity is time and money. And in construction, always, but especially these days, we have very little of either of those. The RSIC Adapt gives you spring performance with RSIC 1 simplicity. So imagine acousticians being able to go to your customers and say, hey, I've got a product that will, I've got a design change, right, option that will maintain the level of acoustical performance that I think is necessary for this project, but it will save time and money, be easier to construct, right? It will solve all of these other headaches. It's got a 6-day lead time instead of a 6-week or a 2-month lead time, right? You would be the hero, right? So try it out on some projects, and I think we're ready to go here. Any questions? I saw a lot in the chat. We got just the right amount of time that I wanted for questions. So good job, Drake. And what questions do we have?
Mike, there's a series of questions in the chat and the Q&A. Let's start with a Q&A.
Sure.
Let's see, starting from the first one, which came from Matt Pose. I don't know if you want to just read that and then respond to it, or I can read it for you.
You read them off. It'll be more conversational
Okay.
with me just reading them.
Right.
Yeah.
So Matthew Pose asked, do you know what the resonant frequency of the Adapt is compared to your spring isolators? One of the advantage, and then he goes on, but I mean,
yeah, okay.
One of the advantages
read the rest of what he said. Yeah.
Okay. One of the advantages of springs is the resonant frequency is much lower, or can be, than would be true of rubber, silicone, or other elastomer-based isolators. This has advantages for low frequency isolation outside of the STC rating range.
Right. So great question. And yes, and this is why we sort of talked about the theory of this, right? And we showed Jerry's thing. So there's the simple answer to the question is, let's see, I've got it back here. Here. So this would be the resonant frequency of this. I think it's like 12 to 14 hertz. A 1-inch deflection spring is like 3 1/3 hertz, something like that. So when you compare the isolation theory of both of these, right? Which is, there's a lot of assumptions that are built into this, right? It's a single degree of freedom mass spring system is how we get these kind of like theoretical isolation efficiency curves for springs, and for this curve for the foam. That, like, the foam with a 12-ish hertz natural frequency will still, in theory, isolate down below 20 hertz, right? A spring with a natural frequency of 3 1/3 hertz will isolate lower and give you more isolation at 20 hertz. But if you actually compare them, it's not huge. I feel like Drake, you and I did this, and we
Yeah,
didn't plot it.
within a couple dB.
It was within a few dB or something like that, right? So it's not a huge thing in theory, right? But then really the proof is in the pudding, and this is why we came and we did all of these sort of comparison tests, and why you get this. And you look down, like we went outside the SDC and IIC range. We went down to 63 hertz, and I don't know if we've got any questions about this, but if there are, I'll address them. We stopped at 63 hertz because we tested at Maxon, and that is the lowest frequency that Maxon is accredited to. That is, and I saw a lot of questions about like why Maxon, why not an independent lab? So one, Maxon is sure not independent, but there's none of their product in this. But they are NavLab accredited, so they are an accredited test lab. They also have the largest, so far, the largest receiving room volume. And so they are accredited down to a lower frequency because they've got more low frequency modal density than anybody else. And so we can get better low frequency data there, which is the thing that we care about for these, right? They also have currently the highest like SDC airborne flanking limits in the United States. Yes, NRC has higher limits, and we could have gone and tested it NRC. I think their receiving room volume is smaller, so they don't have the same modal density. So we've got more issues at low frequencies there with variability. Also, NRC is really slow and really expensive. And in order to be able to go through and iterate these tests, we didn't want to deal with that so that we can do more tests, right? And then also there's been a lot of questions about like, well, what about testing on this or that or whatever? And so one of the reasons is because of flanking limits, right? Like we know we're going to hit that airborne flanking limit, even at Maxon, where their stated lab flanking limit is like 10 points above, Intertech, where most people go test floor ceiling assemblies most of the time. We still hit that flanking limit. So we're still not able to fully differentiate between these isolators, if there is any difference, for airborne sound transmission. So in a couple years probably, so I'm, as many of you know, I'm leaving PAC. This is my last year at PAC. This is sort of my swan song launching this product. I'm going to go be the director of the University of Oregon Acoustics Research Laboratory, where we will have an even bigger receiving room, so we can test even lower frequencies and have adequate modal density. And also, we should have a much higher flanking limit, airborne flanking limit too, so that we can go better differentiate between these. I'm also getting set up to do all kinds of vibration measurements, which we actually got a bunch of vibration measurements at Maxon too, which Drake is looking into, and he's going to present on at ASA in Philly. So if you're interested in all of that, we haven't had a chance to really dive into that, so we don't know what it shows, but you'll find out in Philly as we find out. So there's a lot more testing to come. So I think that answers a lot of different questions that I saw, but they're also like, why didn't you test on wood framed assemblies and stuff? And we'll address that as Steve reads those to me.
All right, thanks, Mike. All right, Matthew Pose went on to ask or comment, to your point on higher spring deflection, like the 1 inch of deflection in a spring isolator, I've thought that it may be true that in these high performance theaters I do, the bass may be so intense that avoiding conduction paths vibrations transferring to adjacent spaces may be better mitigated with the higher deflection. The elastomer systems may do a worse job because the elastomer compression is more like 1/8 to 1/4 of an inch. I have no way to test that. It's just a thought. I will be interested if the Adapt does as good a job of preventing vibration transfer to the upstairs.
So this is the thing that I really wanted to get at with the talking about the deflection and all of these kinds of things. And I think that this is gonna it's gonna take time for a lot of us to kind of like wrap our heads around this way of things, because for so long we have specified isolation based off of deflection. And actually, I don't think he's here. I didn't see his name, but on the list. But I know Eric Miller-Klein has been really involved with ASHRAE. And he and others at ASHRAE are working on changing the vibration isolation like recommendation tables in ASHRAE, moving away from specifying things solely based on deflection and more based on natural frequency. because when you get into these other sort of like elastomeric isolators and things like this, right? Like the deflection is not the defining characteristic, it's the natural frequency, right? There are other sort of mechanisms at play that I will not pretend to fully understand. Oh yeah, I see Brandon CUDA-Quest, ASHRAE TC 2.6 chair, correct. I'm not making stuff up. So there is a movement away from that. And yes, sure, full transparency, right? The spring, the natural frequency is, again, in an idealized, overly idealized single degree of freedom mass spring system, the natural frequency is 3.3 hertz, right? And for the foam, it's like 12.5 hertz, right? And actually, if you go look at that paper that Jerry did, he actually did measure the IFB, a 2-inch IFB, and so you can see those, and you can see like the natural frequencies that he measured for those and those for the springs, right? But the spring, you don't just have that one resonance frequency, right? You have that mass spring sort of idealized resonance frequency, but you also have all these surge frequencies, and those surge frequencies are way higher. They're in the hundreds of hertz, like 300, 400, 500 hertz, and it depends on the coil spring diameter and the spring wire gauge, and then the coil spring diameter and the number of coils and all of these kinds of things, right? So there's like these other resonances, and that's why you get these top offs. And now that happens at higher frequencies, not down at the low frequencies. But again, we don't have an idealized mass spring system, right? We have these two leaves in most of these, right? Where we have, our upper floor structure, or, our subfloor in a lightweight wood frame, like joist construction or something like that. And then we have our ceiling below that. And so you have this mass air mass resonance, this air spring stiffness of that air cavity, right? That also dictates things. And I've seen other people do, papers, Jerry, Ethan Brush with the Syntec, and others have done papers on, floating floor systems where, they'll calculate sort of like, here's, it's a 1-inch deflection spring, here's the expected resonance frequency, but then here's what we actually measured. And it's usually higher, significantly higher than that, because of that air spring stiffness coupling and things like that. And sure, you can vent those kinds of things. And with ceilings, we've got bigger cavities. You're not venting a ceiling, hopefully, because you're trying to seal up all of those gaps because those are sound transmission paths. You do have a bigger air cavity, so maybe that lowers your mass air mass resonance. But there's all of these other factors to consider in this. And the other thing that, and I'll just go on because I think this answers some other questions too, that as I've gone, because like we've done some lab comparisons between springs and clips and other things in lightweight wood framed assemblies. And I saw a lot of people asking like, well, hey, I would love to see this tested in a wood framed assembly, this thing or that thing, right? Joist assemblies, this kind of stuff. So in those assemblies, and even in a concrete assembly, right? The way I've started to think about this is sort of like energy flow through the system. And either way, right, reciprocity says that, if it's energy coming down through it or it's energy going up through it, it should be the same, right? In those, you have, I kind of think about this like as heat maps, right? I think maybe this is where I sort of got this idea, is like looking at building sustainability and, thermal envelopes of buildings for, high performance buildings and things, where you have like the thermal image, right? And you can see the heat conduction through studs and these kinds of things, right? That reduces the overall thermal insulation of the assembly because you get this conductivity through studs. And so no matter how much insulation you have in the cavity, you get all this heat transfer through the studs, through these connection points. So I think we have a similar sort of thing in these acoustical assemblies, right? So if you think about like a typical wood joist assembly, so maybe you've got, some gypsum concrete on the top, your wood subfloor, then, 2x10s, and you've got your spring isolators mounted to the sides of your joists, and then the drywall ceiling underneath that, and some fiberglass insulation in the cavity, right? Well, you have two sort of primary paths, categories of sound transmission through that assembly, whether it's for airborne or impact sound. Right? So if you have the incident airborne sound on the top of that, right, that's making your top floor surface vibrate. And that energy gets transmitted through the structure, through the 2x10s, and then it's isolated by the springs, right, which reduces that structural transmission down to the ceiling. But you also have this other path, which is a cavity path, right? So between the joists, you have your floor resonating, radiating sound into that cavity that then just transmits straight through the cavity and then through the drywall, right? And so if you look at the total energy that's transmitted through an assembly, you have to look at both this structural path and this cavity transmission path. And at a certain point, you will present enough isolation in that structural path where the total energy coming through that structural path no longer contributes to the radiated sound power from the ceiling into the space down below, right? And the cavity path becomes dominant. And once you've reached that threshold, further increasing the isolation of your structural transmission path gets you nothing other than more cost and complexity in your system, right? And it's just cavity path dominated, and changing your structural isolation path gets you nothing, right? And I think that in a lot of lightweight wood framed assemblies, that threshold of the isolation of that structural path is something below springs. And so by specifying springs in those, like, you're not gaining much. And I would encourage you to go look at some of the lightweight wood framed joist assembly tests that are out there, especially ones that have more reasonable top floor buildups, not tons of concrete and things like that that you don't normally get, and compare those to RSIC clips, other people's clips, resilient channel, and I think you'll be surprised at the comparisons that you see. Now, granted, those are lab to lab comparisons. There's a whole lot of big error bars that you should apply to those comparisons, but I don't think you'll see the differences that you expect. All right, rant over.
All right. Thank you, Mike. No, good one. It's all good. All right. Next one comes from Neil Shaw on the Q&A, and there's a comment and a question. And going back to your slide showing the layout for the Adapt, he asks, the layout for the Adapt appears to be different between the interior and the perimeter. This would seem to indicate a different static deflection. How does this affect the isolation?
Not exactly sure, Neil, what you mean different between the interior and the exterior. So it's all the same isolator. The spacing is, it's not all uniform spacing, but the spacing is sort of driven by the typical spring spacing. So, right, so when we're doing, when we're doing a spring layout, we're trying to minimize the number of springs, right? Because springs are not cheap. And also the installation of springs, as I've just talked about for a long time, is not cheap, right? And so we'll typically try and go for a grid of 4 foot by 4 foot. But then when we get to the perimeters, you can't just have a spring, that's got a 4 foot coverage area, and so then it's 2 foot from the wall, because you can't cantilever the steel framing out 2 feet, or just the edge of your drywall will sag. The contractors often want to put L metal there and then tie the framing to that, but obviously that creates an acoustical short circuit. That's bad. We don't want that, right? So we have to put other springs closer to that, so then we have smaller coverage areas. That's why you see this layout here, right? And so in wanting to do an apples to apples comparison and show that you could just do a one-to-one swap between a typical spring layout and the RSIC Adapt, we used this same layout for the Adapt. And so we have the same number of connection points. So in terms of like the energy transmission through varying connection points, that was a variable that we also controlled for, right? And also just like where those are placed, relative to like slab resonances and the modal response of the slab, like all of that's the same, right? Again, trying to control as many variables as possible. So that's why we did the Adapt layout this way, but they're all the exact same load isolator in the same places. So yes, the ones here in the middle theoretically are carrying much more load than the ones here at the corners. So these are significantly underloaded, but that's the point of this, is that you don't have to worry about that and you still get that good acoustical performance. And so sure, maybe we could go back into the lab and do an Adapt layout like the spring layout, where the isolator, stiffness is optimized for the varying loading, right? But I don't think that we would get much additional performance out of that, and that would defeat the whole purpose of the thing, which is the construction simplicity of this. And the question is, does any theoretical or real benefit in acoustical performance at maybe a few frequencies, or a barely noticeable or not noticeable difference in acoustical performance at more frequencies for the springs versus the Adapt, does that small difference warrant the huge difference in cost and complexity for doing springs over the Adapt? That's the question.
Yeah, if I could step in here for a second, this is Mike Gernhardt with PAC. To extend on that a little bit, the whole purpose of the Adapt, like Mike had stated, is to be able to shorten lead times and to get the contractors quicker resolutions for their needs. And if we apply the same principles that we use for springs to the Adapt, we've just added all of that complexity back into the system, except for the ease of installation is still there. But now we've reapplied those layouts and that time constraint that we see a lot on projects. So this is not obviously a direct replacement for springs, but it could be a great alternative.
All right, thanks, Mike. All right, next question comes from Francois Noel. Do you plan to also test for UL Canada?
Yeah, I'll take that, and Mike can just chime in. But so we're gonna go do UL testing, and usually, as far as I know, the stuff that we get, the UL approval that we get in the US also kind of applies into UL Canadian assemblies. So I think the short answer is yes.
Yeah, and I answered it with text. Yeah, when we test, we always test to the more stringent standard, whether it's a US standard or Canadian standard. Sometimes the Canadian standard has heavier dead load on your ceilings when you run the fire test. So we try and always test to whichever one is the more stringent, so that not through Canada UL, but through US UL and ULC, which is different than Canadian UL as a standalone item, allows for transferability between the US and standard construction methods.
All right, thank you, Mike. Next question comes from Daniel Comboni. What are some weaknesses / disadvantages of RSIC Adapt compared to spring systems?
The only weakness I see is that acousticians are going to continue to argue that they need the lower natural frequency of a spring. Like that's all I got. And for mechanical equipment isolation or something like that, where you're closer to this sort of idealized single degree of freedom model of the isolation efficiency and things like that, I think in that case, I will accept that argument. Like if you've got something that's got a lot of low frequency generated noise or vibration from a mechanical piece of mechanical equipment, right? Like sure, maybe springs, 1 inch or even 2 or 3 inch deflection springs make sense in that. But we're not, our world is drywall isolation, right? Is ceiling isolation, architectural acoustic isolation, right? Not mechanical equipment isolation. You can use these for that, sure. But that's not the primary target here. So other than that, I don't really see any weaknesses. That's why we created it.
So Daniel, we also have some unshared data here where not only did we do the standard ASTM testing, but we also did a bunch of vibration recordings. So that is a whole nother line of data that Drake and Mike get to process. So there may be more answers to that question in the near future.
Yeah.
All right. Thank you, Mike. Next one comes from Henning Schlechtring, if I can see the name there. How does the pricing compare to spring hangers? And we had another question from Grayson Steckling on the same. Yeah. Mike Gernhardt, you want to comment on pricing?
Sure. At this time, the Adapt will be priced very similarly to the springs, within pennies, more than likely, to at least the pack series of springs.
All right. Thank you. Next question comes from Francois Noel. What is the strategy with RSIC Adapt for supporting heavy point loads?
Right. So just add more, essentially, right? So it depends on what how heavy the load is and things like that. But so this is similar to what we do with the RSIC 1, right? This is the whole RSIC 1 simplicity thing, right? So if we've got a RSIC 1 ceiling now, typically we say you're using, a light gauge, 25 gauge, 18 mil hat channel. So putting point loads into that is a bad idea because the allowable screw load's like 19 pounds. But if you've got like a can light and a gypsum board box for a can light or a speaker box or something like that, right? You just add some extra RSIC clips and hat channel around that to hold that more concentrated load. Same thing with the Adapt, except with the Adapt, you have the benefit that you can use heavy gauge steel framing, so you can really take those point loads. So if you've got, an 80-pound chandelier, right, that's going to go somewhere, right? Well, then we got an 80-pound capacity RSIC Adapt. You just put one right about where that mount is going to be, right? Or you could put a couple so that you can do framing between them. And if you overspring it, right, you've got more load capacity there than is necessary. Again, in the acoustical testing, we've shown like having very underloaded isolators doesn't seem to affect the performance. Still gets you good acoustical performance, right? And having that extra stiffness there isn't going to like pull your ceiling up like it would with springs, so you'll still get a flat ceiling. So you just add isolators to accommodate the additional load.
All right, thanks, Mike. Next question comes from Nathaniel Cromie. Have you tested Adapt performance with different loads to understand how different ceiling conditions would affect expected STC/IIC?
Slightly, and we're waiting on more of that. So we did test it with a single layer of drywall. We didn't test either of the springs with a single layer of drywall. And we didn't present that data, but we'll have that data. We're still waiting on like the final test reports, and so all the test reports for all of this will be online in our assembly selector as soon as we get it. So we did see a difference in both, I think, the TL values and the ISPL values between a single layer and a 2-layer gyp ceiling with the Adapt. But the difference was about what we would expect from mass law, which makes me think that there's no loss in isolation efficiency, right? Like I would think if the isolators were underperforming because they were way underloaded, we would see even a bigger gap than what we would expect from mass law. But we are doing another round of testing at Maxon where we have an isolator with so the isolators that we tested, the foam that we tested was selected to hold the load of 2 layers of drywall in the largest coverage area, right? Where it's like 16 square foot coverage. So it's an 80-pound isolator. The test that we're going to do is a 160-pound isolator. So even at the max load, it'll be 50% of the ideal design load, right? And so in that case, we're going to test again with 1 layer and 2 layers of drywall to see when we really underload the isolators, what happens. And if in that case, like we get the same results as we did with these that were more ideal loading, then the loading matters even less. And then you can really sort of like overspring things. And then when you have concentrated loads, just like make sure you've got the framing there that can handle it and you're good. It gives you tons of flexibility. So we'll see how that one comes out. As soon as we get the data, we'll do another webinar and present on it too.
All right, thanks, Mike. Adam Adelsberger, I think you might have touched on this already. He asked, why did we do our testing at Maxon?
Yeah, higher flanking limit, larger volume. And then, we're going to come back, like I said, if we're going to test at U of O, which will have even higher flanking limits and even bigger volume. But also on the flanking limits, like I also just want to point out, right, like that this is a test lab that is designed for high levels of sound isolation, right? It's designed to be able to test high performance assemblies, and we're still getting flanking, right? Like this is a test lab designed by Jerry Lilly, and the construction was overseen on a daily basis by Evelyn, right? Like because it was like steps from her office. So it wasn't like she had to go drive to a site to go do construction admin, site walks and all this kind of stuff. She like walked out of her office, walked down the hallway and was like, wait, why are you doing that? You can't do that. Like change this, like all of these kinds of things, right? So there was a high level of, construction oversight from, a very experienced acoustician, right? And then it was like designed by like the guy for designing labs and all this kind of stuff, right? And we still can't get the full performance of the isolators because we've got all these flanking issues and things like that, right? So like it's really hard to do this. And like as I'm looking at the designs for the U of O lab, flanking is driving me crazy trying to figure out all of these details and things like that, right? So like sure, you'd like to hit those really big SDC numbers and TL numbers and all this kinds of stuff, but like I don't know if the isolators are the weak link in that. So let's not put all of our energy there. And I know a lot of the people in the comments that are asking about these kinds of things are doing crazy bespoke designs where they're doing all kinds of isolation and stuff like that. And clearly they're spending a lot of time and energy focusing on other things besides just the isolators. But I just consider the context of all of this.
All right, thank you, Mike. Let's see, Henning Schlechtring asks, do you think that the RSIC Adapt can fully replace spring hangers, or do you still see cases where spring hangers will be better? I think you've kind of commented minimally on this, but you want to field that?
Yeah, I think that like, so from my perspective, and obviously like, I'm sitting here launching the product, I'm biased, right? But from my perspective, I think most situations the Adapt can replace springs. And I think it's the place to start is actually the lightweight wood frame stuff that we haven't tested, but just because like I've really sort of been unable to differentiate between springs and rivet clips and those kinds of assemblies and things. And because that cavity path I think is dominant, right? So I think that's a place to start. And all of these other places where like, yeah, you really need this isolation, but maybe you don't need an STC 80 and an IIC 80 or something like that, right? But you need something better than what you can get with, regular clips or something like that. You want more isolation than that. Or just the extra constructability of this system allows you to hang heavy point loads and all this kind of stuff because you can use heavy gauge steel framing for your ceilings and things like that, right? There's other sort of construction advantages of this other than just the acoustical performance. So I would use those. The place where I think it's going to take the longest to get adoption for this for us is like high-end condominiums, places where there's the highest liability risk for acousticians, because springs are still seen as like the de facto standard and the highest performance. If you do anything other than that and you have an issue, which I don't think you would have an issue with the Adapt itself, but if you did for any reason, right, then you might be worried that you're going to get asked, well, why didn't you do springs? Because those are the best. Again, I disagree with that statement, but I think those are the places like it's going to be the fear of the uncertainty, which is another thing that I've spent a lot of time talking about, is the uncertainty. Let's embrace the uncertainty. Go see all of my other webinars and ASA and NoiseCon presentations. But that's the thing. But I think in most situations for architectural isolation, where we're isolating ceilings, I think the Adapt makes sense as an alternative to springs. Mechanical equipment, different thing, different conversation. And that's not our primary target here.
All right, thanks, Mike. Next one comes from Stalin Vera. If there are ceiling points with higher loads, how can all Adapt hangers be the same throughout the ceiling without having greater deflections?
Because when it's fully loaded, you only get an 1/8 of inch deflection. And so if it's unloaded, it's only an 1/8 of inch difference, right? So it's because of the minimal deflection, you get minimal ceiling height variation because the foam just works differently than a spring. I think I've talked about that enough at this point too. So.
Okay. Thanks, Mike. Next one comes from Carl Peterman. What is the longevity of the foam material? Does it compress over time, years? And how was that tested, confirmed, thinking about cork, he says?
Yeah, great question. So this is Kreiberg Vibrafoam that we are using. Like, we're a US distributor for them too. So this is the same material that's used for whole building isolation and rail vibration isolation and stuff like this, right? So this is put like under the ground and whole buildings are built on top of it. And they've got a long history of doing this in Europe, things like that. And those are much, more extreme environments for it, things like that, right? There is, and I don't know the numbers off the top of my head, but they do have, I think, creep studies on this and things like that. But there's minimal creep, and in terms of where else this material is used, this is an easy application for it.
All right, thanks, Mike. Yeah, Shean Tibbs asked the same question, data on foam creep over time. So if that's something that we have, we could share. I don't know.
Yeah, I'll have to go dig that up.
Yep, okay. Next one comes from Sasi Nak. Is it possible for us to receive a copy of the lab test reports?
Yes. So like I said, still waiting on the final versions of those. We're just, pinning down a few details. And so as soon as those are available, we'll put them up on our assembly selector. And so, Steve, if you haven't already, if you would put a link to that in here, you can go. Yep. If you're not already registered for that, go there, and we'll have this test data, and then whatever other test data we get, we'll put that up there too.
All right, perfect. Yeah, I'll put that link up here shortly. Next question is from Adam Adelsberger. Ceiling size at Maxon versus NRC. Do we know that?
Maxon is nominally 10 by 12. I think NRC's, shoot, they're building a new lab. I think their current lab is 13 by 16. I think.
Mike, do you want to touch on, I wanted to mention this earlier, but why we didn't test at NRC other than the reason that they've, over the last, I guess, almost 2 years now, they've moved away from for-profit testing and moving back towards a research lab. Also, can you touch on the inability to repeat the tests that they have?
Sure, I can go into that. So
briefly,
we have,
if possible.
Yeah, sure. Okay, fair enough, boss. So we have talked to NRC about testing our springs, and then in the past about testing at NRC, right? And we've gotten quotes to do it and all this kind of stuff, and that's when we decided that from a business standpoint it didn't make sense. But in those, I have also talked to their acoustic lab director now, and he has said, because I've said just like point blank, like, look, I want to come in and I want to test our springs and I want to compare to this old NRC test, right? Like, if I came in and I tested that exact same product, that exact same assembly, like, can I repeat these results? Because I want to redo these tests, right? And the answer that I got was, no, we can't repeat those results. They're old, as Drake pointed out, and there's not great documentation for how they were done. And so the results that they get now for springs out of NRC tends to be, at least for airborne, I think our IIC results are actually like fairly comparable for our springs to what the old NRC report has. But for airborne, they get lower numbers when they test current 1-inch deflection springs there. They cannot repeat those, and they don't know why exactly. Could have been assembly mounting, could have been flanking, all these kinds of things that keep me up at night as now a lab director. So even if we were to go test it in NRC, I don't think we would get the numbers if we ran this exact same test at NRC. I think we would get higher STC numbers, but I don't think that they would be as high as some of you might think that they would be.
Very good. Thanks. Very short, Mike. Good job.
And again, we're going to go test it at U of O, and hopefully U of O, I will have similar flanking limits, if not even better flanking limits, to NRC. And we'll see.
Take that,
and
NRC.
Also, Drake has, NRC is fantastic, by the way. I just no shade on NRC. They are fantastic, lovely
awesome
people. They do amazing work. For those of you who know me, that's understood. But for anybody who doesn't, NRC is fantastic, and part of why they are fantastic is they're like, no, we can't replicate those results. We want to make sure that all of our results are really repeatable, reproducible, and in order to do that, we do things this specific way, and that means we no longer get those numbers. And I think that is admirable, right? So but more testing to come. Flanking is hard.
It is. All right, next one from Stephen Lindsay. What sealing cavity did you use, and what sound bath did you use for your testing? Did you only test one way, or did you test bigger, smaller cavities?
Great question. Our cavity was, I think it came out to right around 13 inches from bottom of concrete to back of drywall, and they were all controlled for that. That was that one that we showed here, right? That red line, you can see the Adapt is on the right, our springs and the Kinetics ICC is on the left, right? So the Kinetics ICC is the biggest one, that set our minimum, our minimum plenum depth, and then we just added, extra threaded rod to our isolators to maintain the same plenum depth. So we controlled for that, and it was all right about 13 inches, I think.
All right, and then insulation.
Oh, and then the fiberglass. I think it was just 3.5 inches of fiberglass bat, and we didn't play with different cavity depths. We might at some point. We can go a lot thinner with ours. We can go a much smaller cavity. I mean, if you look at it, right, like, where's my little mouse, right? Like you can have this right up against the bottom of the concrete. So we could be like half that. So you get about a 7, 6, 7. Oh gosh, I have young kids. Like a 7-inch cavity. With ours. So you can do a much smaller air cavity. Of course, that also might affect your acoustical performance regardless of what isolator you're using, because you raise your mass air mass resonance and that becomes more of an issue.
All right. Thanks, Mike. Next one comes from Seth Tomlinson. What is the deflection of RSIC 1 in a ceiling application? How does the performance of RSIC 1 in a ceiling compare to RSIC Adapt?
Good question. RSIC 1 deflection is maybe max
roughly an
like
eighth. Yeah.
Roughly an eighth, 3/16, something like that.
Mm-hmm.
And in terms of how they compare, I don't know, because we haven't tested it yet.
Yeah, we don't have the same cavity depth with an ADM that we do with this. We do have some testing on concrete, but it doesn't have the same cavity size.
Yeah. We might do that at some point.
And those tests were done at Intertech, so our SDCs are handicapped at 60 to 63, I believe.
Yeah, maybe 60. We got a 64 out of there. So
yeah.
Yeah, and those are done under an 8-inch slab, so not an apples to apples comparison.
Yep.
There's a lot of variability there, so I wouldn't compare those.
All right, thanks, Mike. Mike's. Sam Horde had asked on the chat, when do we anticipate testing for wood and steel frame?
TBD.
TBD. Okay.
Still undecided. We have to determine which lab we're going to test at, and that'll determine our pace.
Yeah.
All right. And then Jose had asked, why does the GA recommend sunsetting 30-year-old acoustical data? What does that do to the fire endurance? Where does this recommendation, where's this recommended? I guess he's saying.
So that is from our good friends Ben Schaefer at Pavco and Andrew Schmidt at USG. But the idea being that drywall has changed over the years. Construction materials, test standards, the way we do the background adjustment, and all these kinds of things have changed in that time. And so that's sort of a best practice. And then the I'm trying to remember, it's in the GA manual somewhere. I can't remember where it is. It's in the acoustics section, I think. But then also the ICC G2 2010 guidelines for acoustics or whatever, which is ICC, the International Code Council. This is a supplementary document on acoustics that the International Code Council put out, where amongst other things that they say that the code minimums are, they imply that they're not acceptable because they say STC and IC55 are acceptable, which always cracks me up. But in there, they make the recommendation of sunsetting acoustical test reports that are more than 20 years old. And yeah, I would say that the two big reasons for that are just like construction materials change over time, right? I mean, this is Jose from Dietrich, right? Like EQ studs change, from year to year, oftentimes, right? As you guys continue to innovate and come up with, better products and things like that. But drywall also has changed a lot over the years, and just our testing methods and things like that have changed, as we talked about with the NRC tests.
All right. Thanks, Mike. There was some back and forth in the chat from Grayson Steckling about what is the cap on pounds per square foot for ISO layers per spring. And Mike Gernhardt commented, 650 version holds up to 10 pounds per square foot when spaced at 4x4. Focus loads add additional isolators or adjust spacing for heavy ceiling systems. This is usually the limit for the rest of the framing CRC channel, so spacing may need to be adjusted based on the other steel parts. And then Brandon Kudaquest, who has actually left the presentation, he said, would love to see testing efforts to go into characterizing the dynamic stiffness and performance of the isolator for under overloaded conditions, similar to Jerry's INCE testing. For high STC IIC assemblies, lab testing just reinforces that these are high-performing systems without really telling you how the system will perform under field conditions.
Yeah, so
Yeah.
a lot to say. I mean, like good points, and all of these, like, there's a lot of great questions, and I mean, there's a lot of super sharp folks in here. It's great to have everybody here and have all of these questions and things, and I look forward to all of the discussions that we have after this too with everybody. So Jerry has done, actually, in his NoiseCon paper, he has some measurements of our 2-inch IFB, so same foam material but in a 2-inch version. So there's that. Also, Kreiberg has an online calculator for their foam where I can go in and I can do calculations. That's how I figured out, you know, the material optimization for the different loads and things for these. And so I can go model the shape and size of this with the hole in the middle and all this kind of stuff and look at what the sort of theoretical natural frequency and isolation efficiency curve is for different loadings and things like that. So I can get that. I am also interested in doing some measurements of just the isolator itself. We've talked about doing that, but again, like, this is a component in a system, and it's how this component performs in the entire system that really affects the results that you get. And I'm not sure how predictive sort of a measurement of the isolation efficiency or things like that of just the isolator would be for a whole system performance. That's something that I want to try and figure out. So more to come. We'll see.
All right, thanks, Mike. Let's see, Matthew Pose had commented, didn't your data show that your own springs still had notably better performance than the Adapt, but that the Adapt equals the spring isolator from Kinetics? Meaning maybe the spring is still better if you need the absolute highest amount of isolation, though I already hear you mentioning the limits of the rest of the structure.
Yeah.
Yeah.
Thanks, Matt. Yeah, good point. So I guess one thing I would say to that is, like, yeah, so if you're still insisting on using springs because they're a little bit better than the Adapt at some frequencies, then you should use the PAC RSIC SIFF, because it's even more better. But that being said, often the reason we're using springs is for low frequency isolation. And at low frequencies, like on this for the heavy hard impact, sure, the Adapt, the impact sound pressure levels were slightly higher at low frequencies. All of them are less than 3 dB. They're in the sort of like barely noticeable or not noticeable range, right? And then at the like mid and high frequencies, you know, where we see more differentiation between the products, you can attenuate those frequencies. I mean, one, like, this is dropping a 16-pound shot onto this from 0.5 meter high. Now, we did have a 9mm piece of rubber to just so we didn't chip the concrete, right? So that's why you see this kind of high frequency roll off. But typically in gyms, you're going to use something more than that, right? Like, you can get this mid and high frequency isolation from other things. So I'm less concerned about those differences there, but sure, if you want that extra attenuation at those frequencies, then use the RSIC SIFF. Like, I'm fine with that.
All right, that looked like all the questions we have in the chat and in the Q&A. Wait a minute, somebody else is popping in here. Actually, people are dropping thank yous in for the presentation. If anybody else has any other questions, feel free to drop them in.
I saw one from Daniel, and he says, what is the anticipated availability for the UL test report so that we can use the Adapt? I used the Kinetics in the past and no one likes it. So the UL test and all of this, so UL operates on their own timeline. So we're still in early days of the launch of this product. Let me say that. So, you know, availability and all these kinds of things, we will keep you updated on all of that. You know, stay tuned for emails, LinkedIn blast, and all this kind of stuff where we have updates on, you know, product availability, you know, when we can start shipping this, whenever that's going to be, when we get UL, you know, approval and all of these kinds of things. Those take time. So we wanted to get this out there, start the conversation about the acoustical performance and the construction benefits, and then we will go from there on all of the other bits and pieces and documentation that we will do.
All right, thanks, Mike. So we've been here for about an hour and a half. If people still have questions, we can hang for a few more minutes.
Yeah.
Yeah.
We'll hang for a little bit longer. Thank you, everybody. We see we've still got quite a few folks that stuck around for an extra half hour. I really appreciate everybody taking the time out of your days to come. We will be going around, doing Teams meetings with different folks that are interested in this. So if you have other questions, you want to talk to us more about this, feel free to reach out, send me or Drake or Steve or Mike or anybody an email. We can set up a time to talk. Stay tuned for Drake's great presentation that he's going to do at ASA on the vibration data. We'll see what that shows. If it shows great differences, we'll present it. If it doesn't, we'll also present it. Like, we're transparent with our data, right? We're going to show all of the stuff. That's so
we got one more question came in, Mike,
yeah.
From Eric Siegel. He asked about a comparison to the RSIC SIX.
Good question. We haven't done that. Again, lots of testing, hard, to do, hard to, test everything that we would love to test. Mike won't let me spend that much money on testing. And for good reason.
Yeah.
But the SIX I see is a different animal, right? So the SIX works with 25 gauge hat channel. It's great if you've got, a simple flat, 2-layer drywall ceiling or something like that. But because it uses the 25 gauge 18 mil hat channel, again, screw pullouts in that are minimal. So it makes it harder to do all of these ceiling height variations and all these kinds of things. So although the Adapt and springs are more complicated to build because you can use them to support a heavy gauge steel frame structure, it makes it easier to do all of these complicated things like that. So I kind of see those as sort of two different animals. The SIX is more like a, somewhat higher performance RSIC 1.
All right. Looks like no more questions at the moment.
I think everything was, all the questions in both the Q&A and the chat were covered,
Yeah,
either through text or through conversation. So I think we've burned up an hour and a half. I think we've hit our limit. Like Mike had stated, if anybody wants to dig deeper on this, I'm sure Drake and Mike would be happy to get into the nuts and bolts of all of the data, including some lower frequencies. We only publish what is typically necessary, but we do have some measurements a little lower, and then they will be processing over time, probably not going to happen in the next week or two, over time, some of that vibration data. So that should be more interesting when it comes to integrating gypsum board ceilings with some maybe HVAC ductwork or maybe some smaller Fanco units into your ceiling systems, which we don't typically recommend, but because we don't want to excite the whole ceiling with those energized items, but we see it happen quite often. So it'll be interesting to see how that vibration data comes out. And I want to thank everyone for jumping in here and sticking with us over the hour and a half that we've been giving you data and trying to sell you at the same time. So I really appreciate your time.
And yeah, to all of you, we will have a recording of this presentation up on the website. So stay tuned for that if you want to go back and revisit any of it.
Yeah. All right, everybody.
Cool.
Thank you, everyone.
Thank you.
Thanks, Drake.
Thanks, everybody.
Good job.
Thanks.
Good purse swing.
Thanks, man.
Everybody have a great day.
Yeah, take care.